Hi, Max.
Hey, hey, how's it going?
Fine, thanks. You?
Yeah, I'm good. Yeah, no, it's been a good. Yeah, it's almost like mid-autumn festival. I don't know if many people celebrate that, but there was like a lot of events this weekend. So
Really?
Mhm.
How's the weather there?
Today it's nice. Don't talk about the rest of the time. Yeah, it's like we're starting the long descent into really unbearable winter, but it's okay.
And are you from Boston or?
No, I'm from Seattle, so on the West Coast. It's
Yeah, far
very
from
rainy.
here.
Yeah, I know. It's really like, yeah, I didn't realize how far it was until I started flying home for Christmas, and it's like 6 hours. I don't know,
6 hours, yeah.
very long. Yeah. Um,
I went there in 2 years ago
yeah.
when we started working with JWell.
Mm,
I took a course there from JWell.
JWell. Oh, J Powell, the wait, the like poverty group or
No, from JWell, GWEL, JW.
I don't know.
No, don't worry.
Yeah, okay. There's a
I don't know how you pronounce.
I also don't know. Yeah. Yeah. Hello everyone. Thanks for coming. Yeah. How's everyone doing?
Hi.
Yeah. Good to hear.
They are still shy.
Happens. Yeah. I mean, I think no one really likes talking on a Zoom call, so it's fine. Yeah.
So
Yeah. While we wait for other people to join the class, but yeah, if anyone has any questions about the course content or about like the homework or anything that's going on, we can talk about that now. Amazing. You guys are all geniuses. Got it all figured out. Yeah.
I didn't start the last part, but
Mm,
no, I don't
yeah.
know the rest.
Yeah. No, it looks like, I mean, yeah, this course takes a lot of time, and especially that first problem set, it really just takes you by surprise. So yeah.
Especially because English is not our first
I know.
language.
Yeah, I'm so impressed that you're doing this in a language that's not your native language. I cannot. Yeah. So
yeah,
the English is quite difficult for getting the paper and
I
reviewing.
know.
It's complicated. Yeah.
I mean, the papers are often difficult for me to read, so it's yeah. I think yeah. There's the English and there's also like the math, and the way that scientific papers are written is not always clear. It's
Yeah.
yeah.
I had to be very concentrated and several times read it and read it and read it, and a bunch of time spent on that.
Yeah. Well, I hope it's yeah. I hope you learned something. I don't know. It's yeah.
Not for reading and writing writing, and for me it's hard.
Yeah. No. Yeah. Well, there's more where that came from. I think there's less reading later in the course. I think we don't ask you to like read more papers later on, but there's going to be a lot more like writing assignments. So yeah. Yeah. I think that yeah. So I'll be also like giving you more feedback about the writing assignments. So you get the peer review component. So you hear from like the other students in the class, and then I'll also be reading your assignments, and yeah, we'll try to find some time to like discuss the responses one-on-one too.
So we are going to submit the responses tomorrow, and you are going to give us the feedback in this week.
Yeah, so I don't know exactly when. Okay, so okay, we can refer to the schedule online. So yeah, the deadline is, I think it's Wednesday morning for you technically.
Yes,
but
it's Wednesday, 9 a.m.
Yeah, but that seems like, well, hopefully you're not working on it right before 9 a.m. So yeah, probably tomorrow night would be good to finish that. And then yeah. Yeah, so I don't know when I'll get the responses. They haven't told me that yet. But we'll be, yeah, definitely by like the time that you get the peer review responses back, I'll also have given you our responses. And I hope to have read them by next week's class so that we can talk about them during class time too.
Okay.
Yeah. Marta, thanks for joining. Great. Yeah, we were just talking about the upcoming deadline this week for the writing project. So yeah, just making sure you're aware of that deadline. Yeah.
Max.
Yeah.
Adapt that arose today. We know that the writing assignments, the qualification, it's made up on 3 reviews, but it's an average of the 3 reviews, or how do you, how it's going to be calculated?
Yeah. So it's an average of the reviews unless there's a lot of disagreement. Like if 2 people gave you a 10 and 1 person gave you a 5, then we would then one of the staff would read it and make a final score. But generally it's
just
yeah, it would just be an average mostly.
Thanks.
Yeah, good question. Yeah, and your scores will be computed a bit differently because they're also going to take our feedback into account. So yeah.
And that scores we're going to see on edX.
Yeah, that's a good logistic question. I'll write it down to ask our staff about that. I don't know how we'll be sending our feedback to you. Yeah. Thanks. You'll see the scores from everyone else on edX, but I think our scores might come differently. Yeah. All right. All right, well, does anyone have any other questions about, yeah, like the workload, upcoming assignments, any of the material that's been confusing?
No.
Great, okay. So I'm going to start today with an example from, just to recap from last class. So yeah, we left off talking about regression, and I think you all got to the point where you were running regression, and yes, which I don't know. Yeah, so we were running this regression on the house price data set. So I think everyone got to this point where we generated, oh, not that point, sorry. Yeah, so everyone got to this point where we have just a regression of these covariates on the log of house price. And so you see that some of these look like they're pretty significant, some of them look like they're less significant. So to kind of tie in this with some of the multiple hypothesis testing questions, what would be a problem if you were interpreting these as hypothesis tests for the question of whether or not this variable is correlated with your outcome? So whether or not there's a driveway in your house is correlated with the outcome price or the price of your home. What would be a problem with just running all of these tests? Sorry? Someone's saying something. So you have this column here that's giving you p-values. So if this is a hypothesis test, this is giving you the probability of, incorrectly, sorry, yeah. So it's giving you the p-value associated with the hypothesis test that this variable is correlated with your outcome variable. So what's the problem with just using these p-values? Can someone summarize it for me?
It's like the errors are accumulative.
Yeah.
You test multiple hypotheses at the same time.
Yeah, exactly. Great, thanks. Yeah, I think we covered this last time. So yeah, you're testing multiple hypotheses, so your probability of seeing one of them right is more than is going to be more than whatever the specified rejection threshold would indicate. So this maybe is not so significant here. You have like 10 variables. That's not really where we think that. So this is where we think you should maybe start to correct for multiple hypothesis testing, but you could add a lot more terms to this regression, and then you might see a lot more of a case for this. So in this case, I'm testing this hypothesis with all of these interacted terms. So when I use this in this to the second power in the formula. So without that, this is the regression that we just saw above. But when I add this keyword to make it to the second power, it's also considering all different interactions between your variables. So like whether there's a driveway and also a recreation room, or gas, heat, and air conditioning. So now we're testing a lot more hypotheses. So instead of testing nine variables, we have like 67 different p-values associated here. And so if you want to know like which of these interacted variables are going to be significant, that's a case where it's like less trivial, and you might actually, So this case up here, I would say you probably should, but it's not essential to correct for multiple hypothesis testing. This case, you should absolutely start correcting for multiple hypothesis testing, because you are testing quite a lot of hypotheses. So to just like show you how we actually do this. So first, you can pull the p-values out of your model. So your price model, which is what is fitting this regression to your data, has a lot of different attributes, and one of them is p-values. So this is just an array of all of the p-values from each test. So 67 different p-values for all of your different tests, and the value associated with it. And now if we want to like do this multiple hypothesis testing correction, so you learned all the formula in class, but as always, there are packages that will do this for you. So I'm going to look at this package, the stats models test multiple tests. And you basically, I think I had the import line here. But the format is you just write multiple tests, your p-values, the corrected alpha that you want to have, and then specify a method. So someone tell me so multiple tests are p-values. Alpha, I'm going to say 0.05. And can someone remind me, if I wanted to test, if I wanted to correct for the family-wise error rate, which correction would I use? Which correction could I use? There's a couple options. Feel free to write it in the chat too, or.
Bonferroni?
Yeah, our old friend Bonferroni. So so I'm going to look it up here. Bonferroni, I think we just want the one-step correction, and that's the string Bonferroni. Oh, sorry. Method. Did I spell this wrong? I probably spelled this wrong.
2 R's, 1 N.
Thank you. I always get that wrong. Okay, so when we run the Bonferroni correction, it's saying that all of these are not associated. So Bonferroni is a very conservative correction, but this is saying that we should be careful about, we can't reject any of these hypotheses if we're correcting for all the fact that we're making like 67 different tests. So if instead we wanted to do the, so there's, Bonferroni was one class of corrections. This connects the family-wise error rate. It's a very conservative threshold. The other testing framework corrects the false discovery rate. And so that one was the, Benjamin, so this one, the Benjamin Hochberg correction. So there's also, there was another test that we could do, the Holmes. I think here they call it the Holm-Bonferroni correction. So let's see what happens if we run this one. I think these are the same. It's saying everything is false except that one value. And so the other correction we can run is to correct the false discovery rate. Wow, and here it's also saying everything is false. So good to know. Nothing matters when you're selling a home. We figured it out. What do these results tell me? They tell me that my model is very poorly specified, and that I shouldn't be thinking about these interactions as things that are significant. So this model where I wrote down where I said that your price is probably determined by your driveway interacted with whether or not there's a recreation table. These results are telling me that actually these variables that I'm including are unlikely to be significant for the overall home price. So cool. I just wanted to show an example of how you would actually use these corrections, because I think they can seem a bit abstract, but actually it's a really concrete and easy thing you can do. Once you get p-values from a test, you just plug them into this package, and then you can apply the corrections that we studied in class. So great. At this point, we're going to start covering some other content. So I'm going to move us to my tablet. Okay. So today, why does it always give me more information than I want? Okay, so today we're going to be covering a couple topics on paper. So first, oh my God, okay. I need to charge my pencil. I always forget to do that. Okay, so we're going to be covering a couple topics today. One of them is gradient descent, which we started talking about, which I thought we might start talking about last time, but we didn't get to it. So we're going to talk about gradient descent a bit, and then we're going to cover regularization and model selection. And if there's time, we'll start looking at eigenvalues and eigenvectors too. But see if we get to that part. So let's see if there's any charge. Okay, so gradient descent. Cool. So the goal of gradient descent is, at least in this class, is motivated by regression. So before, when we said that we had a regression framework, we were trying to estimate some beta value. And we said that this was going to be the value that minimizes some loss function that's a function of your data and your parameter guess. So this is, so your loss function is something that depends only on your data and your parameter, and it's something that is minimized at the true value of the parameter. So for ordinary least squares regression, there was that convenient closed form that we found where it was something like beta hat equals x transpose inverse x transpose y. So this is really convenient for most cases. There's not going to be a closed form. Like if you have a neural network, there's no closed form expression for the result. And even for something simpler like lasso or ridge regression, there's not going to be any like a closed form expression that you can use. So we basically have to turn to gradient descent. How does gradient descent work for like solving a general regression expression? We specified this loss function. So this is the function that we want to be minimized at our preferred parameter value. And usually this is something like the difference between the true values of the data and your best guess of the data. So that could be x times your parameter guess. And then we're going to take something like the L2 norm of this data. So you're having some function, and this is going to be minimized when your guess about your function is closest to the true value. So this is the most basic expression for the loss function. And in the regularization part of today's class, we're going to be talking about loss functions that incorporate some other terms. So one of those other terms is that you can have an L2 norm applied to your beta vector. So this is going to say that you want to, if two solutions have the same value here, you would want one that had a lower sum of squared terms in your beta values. So you're preferring terms with lower values in beta. So this is going to prefer solutions with like fewer terms. So that's helpful. So this is something, sorry, this expression is something that if you're trying to minimize this with respect to beta, you can easily find a gradient from like basic calculus in linear algebra. So this is going to be like -2x y minus x beta hat plus the derivative of this term, which is also going to be, which is also going to be 2 times beta. So we can find the derivative of our loss function with respect to beta. And then the intuition behind gradient descent is that we know also from calculus that the loss function will be minimized when two conditions are satisfied. The first is that the first order condition is that the first derivative is equal to 0. And the second order condition is that the second derivative is going to be less than 0. So is that right? Sorry, if we want it to be, if we're trying to minimize, the second order condition should be greater than 0. So that tells us that our function is concave. It looks like this. And if we're finding a point where the derivative is 0, it's going to be the minimum of the function. So ideally this function would be globally convex. So that means that like the curvature is always going to be greater than 0. Of course, that's not always going to be the case. And so you might have a function that looks like a bit more complicated. Here, you can still find the true minimum of the function, but your algorithm might terminate at some other different points too, because if you're just looking for places where, if you're looking for places where the first order condition is satisfied, there's going to be a few places. And these conditions don't let you differentiate between these two places. So you could tell if you were here, the curvature is negative. So this is not a minimum. But if you were here, the curvature is positive. This could be a minimum. This is a local minimum. And here, this could also be a local minimum. So gradient descent doesn't distinguish between global and local minima. All right, so talked about what this is. Yeah, so this is actually a method. So we talk about this method mostly in the context of like methods where you can easily take a derivative. What happens when you have a more complicated function? So if you had a neural network and you were trying to find the whole set of parameters, so all of your different model weights that minimized your training error or whatever you're trying to minimize on the function, how would you, and if it was difficult to find these derivatives, how can you find the derivatives? I guess. Like if it wasn't possible to do this by hand, what are other approaches that you can use to find derivatives like this? Yeah, so I'm seeing a lot of confused faces. So I'll try writing it down out here. So gradient descent works quite generally. But yeah, sometimes the calculus can get like very cumbersome or confusing, and sometimes your models might not even, I don't know. It might be like very hard for you to like write down what these equations are. So what do you do when you can't take an analytical derivative? So like a simple example of a case where you can't take an analytical derivative is something like this function. So if it's a v, the derivative at this point in the middle is undefined. So we can't look for a place where there's zero gradient, but we can still try to minimize this function using gradient descent. So what can we do instead?
So you can move towards the minimum in the direction, on the opposite direction of the gradient. You
Right.
can just move in different iterations and see if you come close to the minimum.
Okay, so yeah. So thanks for that suggestion. So that's like, sorry, I should have said that earlier. That's the whole goal of gradient descent is you start from somewhere,
Okay.
you take a step in the direction opposite the gradient, and then you move closer to this minimum. So if we keep doing this, we keep moving closer. But
your question is when you can't find this direction, you don't know which direction to move.
Or when you can't find it analytically. So you can't take the derivative of the function to find it. Sorry, you like can't use the rules of calculus to do this. Yeah. Well, okay. I was kind of curious to see if you had covered this in other classes, because I think this is kind of an advanced topic. So yeah, this is usually where people leave off in gradient descent. You take the derivative, move one step forward. Most of the time, that's what you do. But when there are these cases, for example, in a lasso model, you have a term that's an absolute value of your beta parameters. So you can't move towards it. So there's, there's one approximation is like to use a numerical derivative. So this says that you evaluate your function at x plus some little amount, and the difference of x minus that little amount. So if you were trying to find the derivative at this point in the middle, a numerical approximation would say like, take the value here and the value here, and divide the f values by the distance, and that tells you approximately the derivative between these points. It gives you the slope of this line between them. So we would divide this by 2 delta, and this tells you this is a way to approximate the derivative when you can't compute it. There's some other, so there's some other fancy like set theoretic notation for these things, but a lot of them boil down to using a numerical derivative when the derivative is underspecified. And another thing that I think I should discuss is automatic differentiation. Which is basically any function that your computer makes. So when you have neural nets, you have like these like complicated functions with lots of weights, and you're doing who knows what, like addition and some sigma function, like, I don't know, adding all of these things up to get to your final answer. So going from x to y is a much more complicated process. So you could try to write down like what all of these steps are and then do some back propagation. And it turns out that your computer can help a lot in this process because your computer already keeps track of all of these different steps. In order to like apply any transformation, your computer is making a series of calculations, and those calculations, you can compute the derivative and then you can apply them, and then you can, you can store the derivative while you're making a computation. So this is, this is what's used in practice when you have these like large complicated neural networks. You still are using gradient descent or variant gradient descent, but you never wrote down the expression for all of these things. You're just storing the derivative while you're computing and using that to evaluate the next step. Yeah. All right, so.
Sorry, Max, I didn't understand this way. This way of automatic differentiation is to get the minimum as well?
Yeah, so it is to get it's to take a step towards the minimum as well. So when we're drawing these loss functions, we draw them usually as one-dimensional things. But what a neural net is doing, you have this like big set of weights. So some set of a lot of different weights of your function. So you have like all of these different weights of your function that correspond to the like different linkages between nodes or hidden layers or your inputs and outputs in a neural network. And so the goal of training the neural network is the same goal as what you're doing up here. It's to minimize, you're trying to choose this set such that the loss function of your data and this set of parameters, and this set of weights is minimized. So we always draw the loss function as a one-dimensional, surface. But the math of this generalizes to like high-dimensional surfaces. So so when you're thinking about taking a step, it's easy to draw it as taking a step like this way along a surface. If your surface, I'm not great at drawing two-dimensional surfaces like most people, or sorry, three-dimensional surfaces, but you might have something that looks more like a cone in 3 dimensions. So this is, imagine this is like a bowl with some minimum here. If you start at a point somewhere along the surface, you can still compute a gradient from that surface, and then take a step in the opposite direction of that gradient.
Okay, so here is, we are getting the minimum of all the W's, of all the weights.
Yeah, so you're trying to find the minimum of all the W's. So here your W's are your beta vector in the notation that I had above.
Okay.
It's the parameters that you're trying to minimize. And yeah, so the goal of training a neural net is the same as the goal of regression, and it's to minimize your error on predicting Y values.
Thanks.
Yeah. So yeah, so that's kind of what I wanted to talk about gradient descent. There's a couple, yeah. There's just one other point that I wanted to touch on, which is the point of, so to expand on this point of like when gradient descent works and doesn't work, I already kind of mentioned that like gradient descent can't tell the difference between multiple local minima. The requirement of gradient descent is that the surface is weakly convex. So this means that the second derivative of your loss function with respect to beta is greater than or equal to 0. So a function like this v, where it's like the absolute value function, this is a function where the second derivative is exactly equal to 0, because the first derivative is a constant on either side of this value. So this is a function where gradient descent will still work. You can still find this minimum, but it's something where the gradient descent can be slow. If the function is weakly convex. So when I say weakly convex, I mean the case where the curvature is equal to 0. And to kind of illustrate that, like you can imagine if you're taking a step from this direction, you might step like entirely to the other side of this V, and then keep stepping back to the other side of the V, and that's going to take a lot more time than if it's a more gently curved function. And here, your steps as you get closer to the V are going to be much smaller because the first derivative is decreasing as you get closer to the 0 location. Cool. So at this time, I'm going to send out a brief poll. Yeah, so I'm going to send you 2 things. First is the link to the doc that has all the links we'll be using today. So this has the Colab notebook I just showed you and the all of the polls. And the second link is going to be the first poll, just about gradient descent. So I'm sending this to the chat. And yeah, please fill out this poll about gradient descent. And I expect this to take about 5 minutes. And then we'll discuss the results.
When you ask minimum, you ask global minimum.
Yes, so I'm asking global minimum, but assume that the parameter only exists between -3 and 3. But yes, global minimum, but you're only looking between -3 and 3.
Only looking.
All right, I still only have responses from about half of you, so I'm gonna wait for another like 30 seconds or so. All right. Yeah. So thanks for those of you who filled this out. We mostly just do this to make sure that yeah, that I'm not being too confusing, which it looks like there's not. There's pretty widespread agreement about these first two. So the third one, it looks like there's some question of whether or not gradient descent would converge to a minimum. So the third example looks like this. There's this pointy thing in the middle. So does someone want to give an argument for or against this? So why would gradient descent not work for this case?
I wasn't sure here because, well, here you mentioned that the derivative could be 0. So in that sense, well, it could be discovered at minimum. But then afterwards, if you see at the left at the -3, that's not a convex. So you could be stuck over there in that minimum local.
Yeah. No, good point. Yeah, so yeah, exactly right. So you can get stuck in the local minimum or local maximum on the left if your algorithm isn't checking the second order condition. So if yeah, so there are some ways that you can modify gradient descent so that it adjusts the step size based on the curvature. So I can talk about that for a second, which is, yeah, so if you're at a case, so if you're at a case where, let's say you had a function that just looked like this, and these are all of your parameter values. If you're at a point over here, the curvature is going to be concave. So that means that you know by a second order derivative test that you're not at the minimum, and you can then yeah, so you can adjust. So there are algorithms that have like adaptive step size. And one of the simplest ways to do this is based on the second derivative. So adaptive step size means that instead of just like taking the derivative and going in that direction by the same amount each time, you can adjust the amount that you go in that direction based on the value of, based on some value. So either some popular algorithms say that you like start by taking big steps and then you take smaller steps. Or another approach would be to compute the curvature at your location and then adjust the step size based on that. So if the curvature is negative, so if it looks like you're approaching a global or a local maximum, then you actually, your algorithm can be smart enough to move away from that point. But yeah, so that was a great observation about this figure, that it might get stuck at the local maximum, but there is a workaround for that. So yeah. Great. Well, yeah, so other than that, it looks like you're paying attention, so I'm pretty happy with that. So at this point, I'm going to stop sharing this screen and start sharing my other screen again, just to go through a brief demonstration about gradient descent. I mean, yeah, I think this is something that really does come up. It has like a ton of practical applications. There's a lot of places where you need to run this to solve an algorithm, and I think that especially with like the trends with machine learning, it's important to know like kind of how these algorithms work. But anyway, so yeah, this is a notebook that you can look through on your own time. It's the second link in this folder. And I'm just going, yeah, so what I've done is I've just coded up a really simple example about gradient descent. See if it works. Great, so I'm just plotting, so this black curve is my function that I'm trying to minimize, and then I compute its derivative. So the derivative is in red here. I don't show the derivative before, but then yeah, you can write an algorithm that takes a certain number of steps from initial guess with some fixed step size. And yeah, this is exactly doing what Marta said earlier, which is just that you take your initial guess of your location, you update based on the step size and the gradient at that location, and then you're updating your location. So you're moving opposite direction of the gradient. So if we started at this location -1, and we took one step, we move this way. So we take the step, compute the gradient, move there. If we take a lot of steps, so if we take 100 steps, we find that we're kind of dancing around this location on the left, which is somewhat interesting. Sorry, if we take fewer steps, yeah, so if we take a lot of steps, we kind of dancing around that final solution. What this tells me is that I need to change the step size, because it's stepping over that final solution. So like I said, if there was a more complex algorithm, you would adjust the step size automatically. Here, I'm just doing it manually, and you see that it does step down towards that solution, which is pretty close to what you would compute analytically, which is -2.417. Yeah. So the risk of gradient descent is that you might get stuck at one of these other like nuisance points. So if we started exactly at 0, we just wouldn't move. We're staying exactly at 0 because the derivative there is 0. That's what our algorithm is doing, stuck at a local maximum. If we started somewhere positive, we would take steps towards this local minimum on the right-hand side, and we would never learn about this on the left. So those are, yeah, so that's, yeah, that's the basic of gradient descent. And then just to like show this on our sample problems. So this first one, really, this is like a great test case for gradient descent. No matter where you start, we're going to get to the solution. And yeah, it's like, yeah, this is exactly how it's supposed to work. It just like takes nice steps down towards the solution. The second case where, oh, sorry, no, this was the second case where it's really bumpy. Like, yeah, I don't know. It's not guaranteed to do anything. It'll just like take steps that are kind of random and might will eventually approach one of these local minima, but will likely not reach the global minimum. And then this case, this is again one where you're going to take steps. If you're in this like nicely behaved portion, you're going to take steps towards this minimum. If you're in this poorly behaved portion, you might get stuck at a local maximum. So great. Are there any questions about this gradient descent content? Okay, great. So at that point, we're going to turn to the next topic, which is regularization. So I'm going to go back to the iPad, share screen, start broadcast. Okay, so next topic, regularization. What is regularization? Regularization is a way of, so it's based on gradient descent, but the goal is that instead of just minimizing the so in the gradient descent that we just saw, you're trying to minimize, like, yeah, well, okay, so what we saw was pretty general, but in a lot of settings, you're trying to minimize like the sum of squared errors. So this distance between your best guess about your function for like whatever generic function you have, and your true outcome values. So you're trying to minimize the sum of squared errors. So a problem can arise if there are, there's a few cases where problems can arise with this. One is if there are multiple valid solutions. So, and a simple case where there's a lot of valid solutions is when you have more explanatory variables than data or than observations. So we kind of, so if you're, so in the home price example, if we wanted to understand the relationship of like, let's say your features are like garage, driveway, lot size, but you only observe 2 homes. There are 2 ways that you can, there are like at least 2 ways that you can perfectly fit your data. Like as long as these things are not collinear, you can perfectly fit your data in a lot of different ways. So you're not guaranteed to get a unique solution. So that's a problem. So another issue where we saw that there are multiple valid solutions is when your data are collinear. So when we saw that example where we had garage and no garage, So in this example, you saw that just doing ordinary least squares failed because the matrix was not invertible. And another, another way of saying that that matrix was not invertible is that there is no unique solution to the problem. So that's one setting where you care about this. Another, and so a solution that you can have is to modify your loss function of your data. So if you had this beta vector, instead of just saying that this is the sum of squared errors, so instead of just saying that it's the sum of squared errors, you add some term that depends on beta. So this is saying, this is letting you choose some solutions you prefer more than others, because they have some function of beta in addition to being a function of your data. So so for example, if our preference was that we only wanted, we wanted the smallest total values of beta, so the sum. So if the second term was the norm, that's the sum of absolute values of each term in beta. This is going to give you more unique solutions to your problem. So it will prefer some variables over others based on whatever the beta values are. So that specific example turns out doesn't help with the case where your data is collinear. But in that case, if you added a sum of the squared terms, this is going to force you to get a unique solution in that case. So so the goal of regularization is you can modify the objective function to incorporate some preference over the parameter values defining your solution. So this lets you distinguish between certain types of this lets you distinguish between some of these cases where you have a lot of explanatory variables, or you have collinear data, or where generally where it's a very high dimensional setting, it lets you find a preferred solution. And this has some key benefits. One of them is that it generalizes better. So when I say this, what I mean is that you'll end up with a solution that has less out of sample error. And that's so you generally want to have less out of sample error if you're doing prediction type tasks. And that's I think that's the basic theory of regularization. You're adding these penalty terms to your loss function. So when you're minimizing the loss function, you're choosing a unique solution, even when a unique solution was not possible before. And that solution can help you in terms of predicting out of sample properties.
Out of sample error means outliers.
No, sorry. That's a good question. So out of sample error. So so out of sample error means you're thinking about error from data that you didn't use to train your model. So sample. So your sample is what you use to train your model. So out of sample is data you didn't see when training model. So to pull an example from computer science, there's a lot of work that's been done over the last few decades on computer vision and facial recognition. So these models are trained on huge data sets of a lot of data on what people's faces look like. They want to be able to recognize a person's face from an image. So you have, I don't know, you have some image, you have something here that looks like maybe this is a face, maybe it's just me being really bad at drawing. The goal of the machine or the machine learning is to do this when you've never seen this model before. So we don't know whether or not there's defaced in this. The model has never seen this. This is out of sample. And you want to have high prediction accuracy. Yeah. So in that case, it's a classification question. Is there a face? And yeah, so that's something where you might know very well in sample, but out of sample, yeah, you're predicting that. And yeah, yeah, we sometimes talk about underfit and overfit models. Regularization is a technique to get less overfit models. So yeah, where that means that they're performing better on data that they haven't seen. And yeah. So yeah, so this is a good segue into a popular technique for evaluating models. So so the technique is like sample splitting, most generally. But the idea is, if you really want to see how well this data this estimator performs on data that it hasn't seen, you should split the data that you have available into training data and testing data. And so this data set is what you're using to fit your parameter estimates. And then this is the data that you're using to report the model accuracy. Because it's not helpful if your model is exactly recreating your training data, but doing very poorly on anything that it hasn't seen before. That's not helpful if you were trying to use this to predict something in the real world, or yeah, to handle cases that your model hadn't seen before. So that's kind of the motivation behind sample splitting. And yeah, so another thing about regularization is that it gives you more so one thing about regularization is that because you have this additional term that you're adding, you can kind of choose how much weight to give that term. So you can add this like lambda value. So we're adding this lambda value at the end, and that controls how much weight you give to this thing. So yeah, if you're trying to penalize having like large beta values in your estimator, you could penalize that by a lot or by a little bit, and that would change the type of solution you get. So yeah, so I'm asking this question now. So how would you suggest that you can choose one of these parameters? This is not something that depends directly on your data. It's like a choice that you can make about your data. How should you choose that value?
So it's what you were talking about. It depends of how much you want to be overfitting your model, or you have to balance between the error and the generalization. The two terms of the loss function at the end.
Yeah. So yeah, balance your error and generalization. Yeah. So yeah. So you're, let's say yeah. So there's another term that I would say you can also think about. So you're absolutely right. So yeah, a lot of the biggest goals for model selection are about balancing error and generalization. Another case is if you care about bias. So yeah, but I'll come back to that in a second. And for right now, I'm just going to talk about these other things. So yeah, there's these two components, error and generalization. Error is something that you can compute. That's like the mean squared error of your model on either the training or the test data. But how do you get a sense about how well your model generalizes? Because the whole point is that we don't have data outside of our sample. So you never entirely know how it will perform on data that's outside of what you can see. So if your goal is to predict something, yeah. So if your goal is to develop this model, set the beta value, not change it at all, and then predict outcome values like outside of sample. How do you get a sense? How can you quantify how well this model generalizes?
So the smaller the betas, the more. No?
Well, sorry, I'm finishing writing. So the smallest betas, or smallest absolute value betas, would just be to have beta equals 0. So this is a model that I'm going to claim does not generalize very well. I mean, it will perform just as poorly in your training data as in your test data, but usually 0 is not the best guess if you have access to other information. So not just, yeah, so yeah. Yeah. So any other ideas about how you can get a sense of how well your model generalizes to unseen data? Sorry.
No, I was saying you still have your betas from the least square term. So it's not going to be 0. It's just trying to keep them as small as possible within the equation.
Well, so let's say in that term, I selected beta, or this lambda equals like 10 million. Like you can make this like arbitrarily large. As this increases, the weight is going to, yeah. So as this term increases, there's going to be even more weight on this term. So we can make this arbitrarily large. This could be infinite. If there's any non-zero value, this term is infinity. And that's going to outweigh any of this error. And then we're going to get a model that's just beta equals 0.
Sure, that doesn't make sense.
It doesn't make sense.
No.
So
You want to
okay,
find out the weights. If you set them all to 0, you don't have any weights.
well, you do have weights. They're all 0. It's a number.
Maybe you can split your data
Right.
in training and testing samples.
Yeah, thanks. Yeah, so I'll address that point first, and then I'll go back to Marta's question to see if we can clear that up. But generally the way that we think about generalization is that you use your test data and say that use your test data and how well your model performs in the test data to assess how well your model generalizes. So in that case from before, if we had like our, if we had our yeah, you can write a plot of your loss function. So, or let's say, so you can write a plot of your mean squared error on the y-axis versus your guess of this lambda value. So if lambda is, yeah, so lambda value. So lambda is 0 to lambda is something like infinity. So on either end, you're going to have like pretty high mean squared error, maybe. Oh, sorry. Yeah. Let's see if I can think about why that is. Yeah, so if you're doing this on your training data, so you're going to have relatively low error for some values in your training data. Okay, let me see if I can like explain more clearly why that's the case. So if your loss function that you're trying to minimize has two terms, it has your mean squared error plus lambda times the magnitude of your beta value. So as we increase this lambda value, your loss function cares more about the values of beta. So if we increase this all the way out to infinity, any deviation from 0 in your beta value would outweigh any of the mean squared error in your data. So then this model, this loss function only cares about this. And if we're selecting beta to minimize this loss function, then you're going to get a value that could be a really poor fit for your data. And then the other extreme, so this extreme where we have this end, lambda equals 0. This is the case where you're exactly or as close to exactly fitting your data as possible. Yeah, so when you're evaluating the training data, you can get some curve that plots the mean squared error versus lambda value. And then, yeah, like as Matteo suggested, you can evaluate separately on test data. So what you'll likely find is that, again, at lambda equals infinity, you'll have like, your model will not perform very well. It'll have very high error. And also when your model is overfit, so when lambda is close to 0 for a Lasso model, you might have higher error. And then somewhere in the middle, there's going to be like this dip in your in your test data. And this is like the point that we would recommend. So this is the point where it looks like your model generalizes the best because it has the lowest prediction error on data that it didn't see when it was choosing the values of beta. So let's see if that's clear. Yeah, so the problem that you're trying to solve with this graph is you're trying to pick this value. And as a researcher, you could choose any value and you could get a model. So the value, like to use statistical language, this value is not identified by data. It's it's not identified by your observations. It's something you have control over. And so the general rule that we use is you want to pick the value that leads to the best generalization as defined by this train test split. So yeah, let's see, how are we doing on time? Okay, so yeah, there's a brief. Okay, so there's one other topic I said I would circle back to this point. So the point is about bias. And the downside of doing regularization is that regularization can lead to bias. So bias is the property. So yeah, bias is the difference between the true value of your parameter and the best guess of your estimator. So the expected value of your estimator. So an unbiased estimator is one where the expected value of the estimator is equal to the true value. So we usually don't know the true value, but if you know this property that your estimator is unbiased, then your estimate is going to be a good guess for that value. So the most widely used example of an unbiased estimator is ordinary least squares. So this is in linear regression, ordinary least squares is the unbiased estimator of beta. And to think about why regularization leads to bias, once you start having this term here, ordinary least squares is finding beta is equivalent to this problem that we've written above, is equivalent to finding beta when lambda is equal to 0. So when there's no weight on this term and you're just minimizing the squared error, then you're finding the ordinary least squares estimate. So when we start moving beta or moving lambda away from this, so when lambda is greater than 0, you're going to introduce bias because because your estimate is differing from the beta that you get with ordinary least squares. Yeah, so so we say we often want estimators to be unbiased and to generalize well. Sometimes that's not possible, so you have to make decisions about which ones you care more about. So when do we care if a parameter is biased? So as you see sort of from this illustration, which a lot of graphs do actually like follow this pattern. If we think about the lambda equals 0 as the ordinary least squares estimate, this is not generalizing as well as other models. You could have a model that finds a better solution to if your goal is to like predict data that you haven't seen before. So when the goal is just to predict something out of sample, you don't, your concern is not about bias. When do we care if there's a bias in a parameter estimate? We care if there's a causal interpretation. So if you really care about knowing using regression to understand the effects of smoking on health or like a vaccine on population outcomes, then you care a lot about that parameter being unbiased because that tells you how much the outcome variable changes when you change that dependent variable. And if that parameter is biased, then you're not getting you might not know how much the outcome variable would really change. So yeah, when there's a causal effect, that's when we really care about bias. And in those cases, you would not want to use regularization. So great. That's all the theory that I wanted to talk about regularization. So does anyone have any questions about this?
No.
Great.
No, it's okay. Some of the things we already studied in machine learning.
Okay, yeah, that's kind of what I would expect. But I also heard
some of them.
Okay, because I heard that the machine learning course didn't talk a lot about ridge. Yeah, so have you seen lasso regression before?
Yeah, I don't remember, but yes, we
don't remember. Okay. Yeah, because I think that's like not a focus of machine learning because you move by really fast, but in statistics, it's actually like people like it because you can analyze the properties really well, and so they use it for a lot of examples. So That's kind of why we talk about it. Yeah, and it helps illustrate concepts that are like statistically like very valid. Like if you wanted to do causal analysis using a neural network, that's something that is possible. But you're introducing these biases because you're applying some regularization to help select for your model configuration in practice. So yeah, so it's easy to illustrate that for like lasso and like this type of model, but it turns out that these same topics about regularization like apply to like any type of estimator. And there's a lot of really interesting research happening right now about how you can do causal inference in settings where you have like a machine learner that might be introducing regularization bias. But that's I don't know, probably not relevant for anything that you're doing. Yeah, we'll see if it ever gets to a point where a lot of people need to learn about it. So, yeah. Okay, well, so if you've already seen, okay, so at this point, I'm going to let you choose the activity that we do for the last part of class. So if you've already seen, yeah, so there's two options. There's two topics that we can explore. I have like a coding exercise prepared for each of them. This one. Yeah, so there's two coding exercises that we can explore. One is about eigenvalues and eigenvectors. This is something that's going to come up in the next class. Or sorry, the next module about genetics, but should be familiar from linear algebra. And then the other one is this example about how you can, how you can estimate, models using regularization, or estimate linear models with regularization. So I think I can. How do I do this? Okay. Well, okay. I'm going to try to find the place where I can add a poll. We'll see. Okay, well, okay. Why don't people, if anyone has a strong preference, please say it in the chat now, and we'll go to that one. And if not, we'll just look at this workbook about regularization. Okay, regularization is okay, great. Yeah, I'm sorry if this is reviewing something that you've seen before. I know I always hate that, but hopefully it's more hands-on, so it at least feels like a different way. Yeah, so yeah, so this time, like we did last class, I'm going to give you a workout and split you into 2 rooms and ask you to fill out the fill in some code that's missing from this assignment. So this time I tried to be very clear about what I'm providing, what I'm not providing. So there's a lot of descriptive text. You can read it. I hope it's helpful. And then all of the blocks of code should be run, and they have a comment at the top. So this one just says import necessary packages. This is just going to doing something standard. In this one, I told you that I've only defined 2 of the functions. So I've given you this loss function and this regularizer, but I'm not filling in the objective function or the mean squared error. So I'm asking you to fill in the code for those. So yeah, I've done that for each of these blocks of code. This one, just run it, no need to change. This one, fill in blocks of code here, and so on. So hopefully that will be easier to follow this time. And yeah, since there's only 2 groups, I'll just be going between the rooms. And yeah, so here's the link to the workbook. And I'm going to split you all into 2 breakout rooms. Yeah, so I'm splitting you into 2 breakout rooms, and yeah, Martine, Cecilia, and I will be going between them as well. So. And Cecilia, I think you're a host this time. Is
Yeah.
that okay? So you can feel free to move around, whatever you think is helpful, or stay here.
Thanks. I'm sorry I was late
Oh, no worries.
because I have a class before 7 p.m. So my teacher doesn't allow me to go out before the ending of the class. I'm sorry.
No, I understand. Which class are you taking?
I'm doing a master on demography and population.
That sounds cool. Wow. Yeah. I don't know much about that.
So what do you think about them today?
Yeah, I don't know. Well, I'll see how they're doing in this coding exercise, because I think that was a struggle last time. But yeah.
Okay.
Yeah, I don't know. I think that yeah. It seems like we're still not getting so many students, which like
we talked today with Natalia,
uh-huh.
with Martin, and probably we won't have all the students in this course, so we don't have a number yet, but we have. I'm talking much more than I am allowed, but I think we have 10 confirmed, and then the other ones are gonna confirm before the month end. So we are probably expecting 6 people every Monday.
Okay.
Sorry.
Yeah. Well, so then we should also we can talk more after the recitation today too, but if the group is very small, then maybe we can think about other exercises that are more helpful, or other ways to talk to the group that are more helpful.
That's nice.
I don't know, because we can be more individualized if it's
more personal thing.
Yeah. Also, what a great student to teacher ratio if there's 3 of us every time.
What? I'm sorry.
A great student to teacher ratio. There's
it's like 2 per.
Yeah. I feel like we could still take them in fact, but anyway.
Yeah.
Oh, wait, this is being recorded. Oh, okay.
Probably the ones that come.
Yeah.
They're talkative.
Yeah.
We commented with them in the last office hours that you're gonna rate their work, or I don't know if rate, but maybe read. I have a question about that, but probably we should ask Karin, because I don't know what to tell them if they ask me how this is graded.
Yeah.
So they have a written report that's due on Wednesday.
Wednesday morning.
Wednesday morning, and they are gonna rate 3. They're gonna do some peer grading and receive peer grading, and then they are receiving your grade.
Yeah. Yes.
And what's the I don't know how to say it. The qualification, the how many points they get from the other students, and how many
we're still working out exactly how many, but I think most of the grade will be from my assessment, and then some of the grade will be from their peers assessment. So.
Okay, so the full points, they're split in two with you don't know how.
Yeah, that's a question for Karine, and we talked about it in our staff meeting today, and we haven't figured it out, but we'll get there.
Okay. I tried to convince them to come to the Mondays classes because you're gonna grade them.
I think that's nepotism. I think that's not allowed. But
Yeah, but it's better to know the teacher who's grading you.
true story. Yeah. Yeah. How are they? How are they doing in office hours? Does it seem like people were
We had
having
more or less the same attendance? There were 6 or 7.
Did it seem like
we,
they were? Yeah.
We had I don't know if 1 or 2 students that don't come to Mondays that we haven't seen this in this course, but they had an only question about something on the homework.
Yeah.
And then we speak mostly about the course and use and how it's gonna be. That is pretty confusing.
It is pretty confusing. I agree. Yeah, this course is, I'm surprised that they adapted it for the online course because it's not one of MIT's best courses. Sorry, I really shouldn't be saying this. Okay, I'm gonna go.
No, it's okay. It's not what we are used to.
Yeah.
Because, yeah.
No, it's very, like, I think its strength is that it's very applied and project based. So when we get into the next module about genetics, I think students have a lot more fun with that module than this first one. It's like actually, they learn to do a lot of really cool things. Yeah, and we want to make sure that they know something about the statistics behind what they're doing. But yeah, like I think like starting next week, they'll start being able to do like very interesting things. And I hope that will be more exciting for them. I don't know.
I hope, and that they're more encouraged to do next module.
Yeah, me too. All right, well, I'm gonna check in on the rooms.
Okay.
Sorry, me tiro para afuera. ¿Me pueden volver a mi breakout room?
Sí, ya te pongo.
Gracias.
A ver.
Uno creo que estaba.
Ay, no.
Con Rodrigo y Edison.
Ajá. Para que te tengo que mover a acá. Asignar a con Edison y Rodrigo. Sí,
Gracias.
deberías poder entrar ahora abajo en donde dice sección. Ahí.
Hey, did your group end up finishing the problem or?
Yes.
Awesome.
Yes. We printed the. No, I think there was a last part.
Yeah,
at the
yeah.
end. Okay. So I think we didn't do that, but we finished it with the errors.
Awesome. So you were like able to like plot the train and test errors and find the minimal value.
No, we didn't plot. We just looked at them and we saw that the training error was increasing constantly and the test error was fluctuating, but had a U shape, I think. It started
that's awesome.
decreasing at first and then increases.
Awesome. That was, that's great. I hope that helped your understanding of like how you select hyperparameters. And just someone from the other group want to share, because you guys worked on the eigenvalue problem. Do you want to share anything about what you guys learned?
Yes, sure. Maybe we can just show the first we.
Yeah. Also, I'm sorry. I realize we're going over class time, so anyone who needs to leave, like, I'm sorry. Feel
so we
free
just
to
plot the data here, like 100 points from a multivariate normal, and then we find the Asian vectors and the Asian values. Then we find the empirical covariance and found found the empirical values and vectors, and then we plot both vectors here with the data.
Great.
That's it.
Can you share the code with us?
Vamos a ver.
I can share my code for that.
I think Max's code is better than mine, but
I think it's very similar. So
I can copy right now.
Great. Yeah. Okay. So I'll put the solutions on that document, and everything will be sent out by Cecilia at some point. So and also, so we're done with class time. I'm sending out a poll again for the end of class. If you could just take a second and let me know, give me some feedback. Since it's such a small group, we can be like very individual about what's helpful for you guys. So please let me know what your feedback is, and I'll do my best to incorporate that into the next lesson.
Perfect. Thank you, Max.
Yeah, thanks everyone.
Bye.
Bye-bye.
Bye.
Bye. See you next week.
See you next week.
Okay.
Okay.
So I was thinking that they were gonna ask something about next the written report, but they didn't.
Yeah, they asked actually at the beginning of class about that.
Oh, and that's okay.
So,
That's okay.
Yeah.
Okay. That's nice.
Yeah.
Okay, so do you have the access to the Moodle course?
Sorry. Oh my God, I'm so behind on emails. I think I saw the link and then I didn't.
It's not yours. It's just for you to have access, so you can see what we share with them.
Yeah.
Maybe talk with them. I don't know. So okay. See you next week then.
Yeah, see you next week. All right, good luck with the upstairs.
Okay, I will encourage them to write to you if they have some specific questions about the written report.
Please.
Okay.
Yeah, do they have my email? They should.
I will write to them with. I don't know if they have your email.
Well, yeah,
but I can
feel
share.
Free to share it. Yeah.
Okay.
Yeah.
Thanks.
Thank you.
See you next week. Bye.
Ciao.